Alrighty, I think we'll get started here. Thank you all for joining today's Data-Driven Science and Engineering Seminar. We'll be hearing from Professor Michelle Girvan today. Professor Girvan is a professor in the Department of Physics at the University of Maryland, where she also has appointments in the Institute for Physical Science and Technology, the Institute for Research in Electronics and Applied Physics, as well as the Applied Math and Scientific Computing program. Her research focuses on applications of network science to biological, social, and technological systems, with much of her recent work aimed at the intersection of network science and machine learning. Today, we're excited to hear about some recent work on brain-inspired mechanisms for robust reservoir computing.
Thanks for that very nice introduction, and thank you for inviting me here today. As I was saying a few minutes earlier, I wish I could be there in person and learn more about your institute there. And so I'm going to talk today about brain-inspired mechanisms for robust reservoir computing. And I know a lot of you won't be familiar with what reservoir computing is, so I'll give you some background on that. But in general, as you heard in the introduction, my recent work is really focused on machine learning meets complex systems. So I think of myself as somebody who applies methods from physics and nonlinear dynamics to complex systems problems. And particularly where networks are involved, where the pattern of connections matters. So I've been working at this interface between machine learning and complex systems for a while, and we can sort of start out by asking, well, how does machine learning help us understand complex systems? And maybe that's the more common direction here. So in complex system science, we think about, for instance, how interaction patterns give rise to system behaviors. That's the network science side of things. And in machine learning, we can use machine learning to help identify interaction patterns that are important in different kinds of scenarios. So ones that we hadn't thought to look for instance. And also more recently, some of my work has been focused on how machine learning can help us predict the dynamics of complex systems. And some of that is going to be in my talk today. But then there's also the flip side. How can a complex systems science approach improve machine learning? So a lot of what machine learning is built on are these large artificial neural networks. And these artificial neural networks are complex systems that have a delicate interplay between structure and dynamics. And in biological networks, for example, the complexity arises in drawing from plasticity mechanisms for robust performance. So that's one place where complexity arises. And we're inspired by that in some of our designing ML schemes. And that's the basic idea that I'll talk about in the latter part of my talk. Can these principles of plasticity help improve robustness in ML models, and particularly in reservoir computing? So a little bit of an overview. We tend to be more familiar with deep learning. Modern machine learning is based on deep learning. And these models achieve impressive performance, as you're familiar with, by optimizing large collections of internal parameters. But the downside is they can require substantial computational and data resources. So in contrast, the architecture I'm going to talk about today, reservoir computing, keeps internal dynamics fixed in a recurrent neural network and trains only an output layer. So that simplifies things a lot, but we still have requirements for what this internal reservoir has to be. Biological neural networks, by contrast, they sort of leverage the inherent plasticity that they obtain over evolutionary timescales to maintain stable that are useful for information processing. And so the idea is, can we draw on these types of principles? So in this talk, I'm going to give you a little bit of compare and contrast between deep learning and reservoir computing and where RCs fit in the machine learning landscape. And I'll talk a little bit about hybrid RC and GRC architectures because I think that might be relevant to some of this audience where we can hybridize different types of machine learning schemes. And then I'll get to this part that I want to elaborate on a bit more, brain-inspired plasticity mechanisms in reservoir computing. So we use machine learn or we use deep reservoir computing a lot in our group, and but it's only going to be appropriate in certain cases, and it's useful to understand when that would be. So let's compare it to deep learning. So deep learning, we have the standard structure where, let's say, we're thinking about image classification. We feed in an image and we want to output its class. Is it a dog, a cat, a giraffe, etc.? So we feed this image and it's processed through successive layers of neuron-like units. It's primarily a feed-forward architecture where arrows point from lower layers to higher layers. Deeper layers perform higher information processing. The weights between the layers are trained via backpropagation. And so all these individual weights are trained. So that's large scale parameter optimization. So these are expressive models, but they're computation and data intensive. So if we don't want to take on that burden of needing so much data and needing so much compute, reservoir computing offers us an interesting alternative. So I don't know why this keeps, okay. Sorry, I'll just say what it is. Okay, so these were independently introduced by Jaeger and Moss in the early 2000s. And what we have here is that instead of having layers of neuron synapses that we train, we have a fixed random network called the reservoir. And then we feed the input in and we only train the output weights, the red links that you see here. And what's happening is that the system is relying on the dynamic complexity of the reservoir to be able to mimic any kind of dynamical system. And so we often use this for time series predictions. Very nice model for general approach for time series prediction problems. So when we think about time series prediction, we have a time series U of t, and our goal is to predict the next time step, U of t plus delta t. And our reservoir is this recurrent artificial neural network capable of rich dynamics. We have these neuron-like units, they're random sparse connections, and the connectivity is fixed at the beginning. So we're not training those internal weights. And we have these internal firing dynamics where we feed the input in, and our reservoir dynamics are such that the state of our reservoir nodes at time t plus delta t is a nonlinear function of the states so it depends on the inputs. The state of a node at time t plus delta t depends on the inputs it receives from other nodes. That's encoded through the adjacency matrix. And it depends on the external inputs that it gets from this input time series U of t. And the feedback loops, the recurrence in this artificial neural network, provide memory in the system, such that the state of the reservoir at any given time depends on the history of what's been input to it. But the simplicity here is that only the output weights are fixed. So we do ridge regression to give the best one-step predictions over the training data. So this is our approximation. So we want our output weight matrix times R to be approximately the next time step for our training data. And the key advantage is that training is simple and efficient because only the output weights are adjusted. So that sounds kind of, really appealing, but obviously, there are going to be cases where it's not going to work, right? This generic system. So what are the important features of the reservoir? So I need it to be an input-output system. And what it does, it's going to project low dimensional input into a high dimensional space. And that's the reason we can use this ridge regression. And we do this nonlinear projection, and it has to be complex. It has to provide a complex repository of dynamics such that when given different inputs, it's going to react in very different ways. So it needs to have a large dynamic range. And but one of the important features of this approach is when we look at it here as a generic reservoir, we see that we can do this in hardware implementation. So there's been, even though I said, okay, reservoir computing was introduced in the early 2000s, there's been a lot more interest in it in the last, 5 to 10 years, partially because it can be implemented it's very fast, can be implemented in simple hardware designs. And has been of interest to a part of the dynamical systems community. So we've been working on various problems in this range. I'm only going to talk to you about a little bit of our work in our UMD group about this, but we've been thinking about combining reservoir computing with meta learning for tailored forecasts from really short time series. We've been thinking about generalization in reservoir computing, noise regularization, using parallel approaches to predict the dynamics of complex networks, and predicting non-stationary dynamical processes with reservoir computing. So, hit me up about this by email sometime if you're interested in any of these types of problems. But our main focus here is building and understanding RC models for complex time series prediction tasks in the papers above. And part of what I want to talk about today instead is, well, how do we really think about the design of the reservoir a little bit more? And in order to frame that, I think it's useful to say, okay, well, where do reservoir computers fit in the ML landscape? So if we think about a lot of modern machine learning methods, especially like large language models, but even simpler deep learning convolutional neural networks, they're on the left-hand side here of my spectrum. They're flexible data-hungry models that have low inductive bias, and what they do is they learn complex behavior from large data sets, but it's really hard to interpret them and interpret their learning. On the other end of the spectrum, we have efficient structure-guided models that can be enormously useful for scientific computing, for example. So they have high inductive bias, and they leverage explicit nonlinear features or structural assumptions. So I have to put those in, but if I put in reasonable things, and even if I don't get it all right, I still fit a model that I can now understand. So in your groups, I'm assuming that many of you are familiar with, well, I know from the University of Washington group, the Cindy model is very nice in terms of what it can achieve in modeling dynamical systems, so sparse identification of nonlinear dynamics. And in a similar spirit, nonlinear vector autoregression, NVAR does something similar, although it's not sparse identification. And then that version of that is also called next generation reservoir computing. So where does reservoir computing fit in all this? It fits in between, I would say, a little closer to the high inductive bias models. So it has intermediate inductive bias, where we're taking this repository of dynamics. So I have a high dimensional internal dynamics, and it generates a rich repertoire of implicit features. So my feature vector here are not the nonlinear functions I put in, but rather the state of my node activations at any point in time. But because the model is highly simplified, I'm only training the output weights. It's fast and data efficient. So I wanted to touch on, because I know that many of you may be using models like Cindy, I wanted to touch on how reservoir computing, well, let me go back to this slide for a moment. One of my interests is sort of combining these different types of machine learning models to leverage the strengths of each of them. And so we had this paper from 2024, which was a hybrid approach combining reservoir computers with next generation reservoir computing. So my reservoir computers, as I said, I have these fixed recurrent dynamics, and that my feature vector there is the state of the activations of my nodes, and it has intermediate inductive bias. It's, you know, easier to interpret than a deep learning model, but not nearly as informative as something like Cindy or nonlinear vector autoregression. It's lightweight, but the performance does depend on like how I build this reservoir network. So if we think on that right end of the spectrum, this on the high inductive bias side, we have explicit nonlinear features, polynomials, delays, etc. High inductive bias, but the benefit of that is I get these interpretable models. But success can be sensitive to feature choices. So our motivation here is what if we have a problem that might need something more like a reservoir computer where these high inductive bias models aren't quite working well. Would the high inductive bias models still help our reservoir computing framework? So this idea is I want to combine this intermediate inductive bias with the higher inductive bias models to see if they have complementary strengths. So with the idea here, we can combine the implicit nonlinear dynamics in my reservoir computers with the explicit nonlinear structure in these more structured models. So here is our hybrid where we can combine the reservoir computer with next generation RC architecture. So what is a next generation RC? Basically, I take my input U of t, and so the next generation RC is like this gold part. So I make a bunch of functions. I have the time delayed observations, and then maybe I have nonlinear functions of the above terms. So at first, I might just take all quadratic terms. And then the next generation reservoir computing just does ridge regression, taking a weighted combination of these terms to find the best fit for predicting the next time step. And here, and as I said before, what the reservoir computing does is it's feeding this into this recurrent neural network, taking a linear combination of the reservoir activation levels, reservoir node activation levels, and fitting it to give the next output. So now what I've done is I've concatenated these two feature vectors together with the goal of achieving the performance flexibility of a large reservoir computer. So in general, with reservoir computing, we often, for low dimensional dynamical systems, don't need such a large model, but the higher dimensionality of dynamical systems, we need more reservoir nodes, more neurons. So if we make this combination, can our inductive bias in the structural models help us and maybe require less compute in our reservoir? And so this is the reference for this paper is from 2024, and I want to note my collaborators, grad student Ravi Chapuri, undergrad Dale Zalag, and my UMD colleague Professor Antonsen. And so just an illustration, this is like a toy illustration showing a case where the hybrid system can be really beneficial. So here we're looking at the Lorenz system, and for these structured models, you might think, okay, Lorenz system should do really well if I keep quadratic terms, and that's what I'm doing in my NGRC. But in this case, we take a longer sampling time for between the time points that we're observing of the Lorentz system, so that this approximation to the Lorentz equations, we're not taking this small little time step anymore. So what we find is that the NGRC itself, even though I keep all the quadratic terms, it doesn't perform very well. Now, this is a problem, the Lorentz system, that an RC can do really well. RC of moderate size, 200 nodes, great predictions. But what if we take a small RC of like 50 nodes? We find that it doesn't do that well predicting the Lorentz system. So we're on the left here, we're showing the long-term phase space of the trajectories of the forecasts. And the hybrid system, we see it captures the Lorentz attractor. And we see, if we look at the power spectral density, that our true system in black dashed matches the hybrid power spectra, whereas it's quite off for the RC and NGRC. And of course, this is just a toy example. But our general principles here from this paper is that we can get a lot of benefit by combining, we can get sort of large reservoir computer performance using a small reservoir and compact NGRC features. And compared to the NGRC, we can handle much larger time increments in our sampling. And compared to the reservoir computer, adding the NGRC or the structural model makes it less sensitive, makes the hybrid system less sensitive to decisions in the reservoir construction. And so in general, we're kind of more robust to weaknesses in either component alone. So we're effectively combining the RC's implicit dynamical richness with the next generation reservoir computer's structured nonlinear feature sets. And so hybridizing, it gives us this advantage. And from the RC side, it reduces this dependence on hyperparameter tuning. So let's get back to that problem about hyperparameter tuning. So great, we reduce the sensitivity to reservoir hyperparameters. And I showed you just like the overall design of a reservoir computer in my generic reservoir. So if that's a recurrent neural network, can I design it in a little bit better way so that it's more robust? What do I want to think about in terms of its internal dynamics? One thing that we investigate in the study I'm going to talk to you about is the excitatory-inhibitory balance in the network. So a little bit of background about how we approach this. So this part is in collaboration with Dietmar Plens of NIH, who has been a pioneer in critical dynamics in the brain. And this is also with our student, Keshav Srinivasan, who really led the project. So what were we thinking about that when we tackled this? So experimental studies suggest that biological networks might operate between a critical boundary where activity dies out and where activity gets amplified. So I'm a physicist. I like these order parameter versus tuning parameter plots. So this critical point is this phase transition between the two. And what is important about this phase transition, if we're close to this critical point, we expect to see a power law distribution of avalanche sizes. So that's if I trigger one neuron, what is the size of the set of neurons that then get affected from this? And so this experimentally was shown to have a power law distribution with exponent given by the theory of critical branching processes. So the hypothesis about criticality in brain networks is that being close to this critical point gives information processing advantages. So if we study this in models, at this critical point, we get maximum dynamical range, for example, which is the range of stimuli that the system can differentiate its responses to. Our question is, can we have systems that achieve some of the advantages of criticality without being precisely tuned to the critical point? So this is what we were motivated in when we started this project. And in particular, this notion of robust critical dynamics relates to some prior work that we did modeling the dynamics of biological neural networks. So we showed that for certain network architectures, I can vary the system, its parameters quite far from the critical point, but still see critical-like dynamics. And so what do I mean by that? Well, if I'm looking at these power law distributions, we see the black line, that's my theory of this power law at the critical point. But if I look at the system B, for instance, the dashed line, if I move it quite far away from the critical point, it's still giving me power laws over many orders of magnitude. Whereas if I move system A away from the critical point by changing its parameters, I'm quickly destroying that power law-like behavior. So our motivation with this was, can we design more flexible machine learning schemes in our reservoir computing framework in particular, to have some of these, to take advantage of critical-like dynamics. So what do we do here? We were specifically interested in exploring the balance between excitation and inhibition. So there's a lot on this slide, and I don't want you to focus on all the details, but basically my reservoir construction is the same as before, is similar to before. But what we do here is we explicitly separate out an adjacency matrix for excitatory links and an adjacency matrix of inhibitory links. And I want to vary my balance. So if you look in this purple box on the right here, I want to say my local balance is for a node, how many incoming excitatory links does it have, or what's the weight of its incoming excitatory links minus the weight of its inhibitory links. And so 0 would be the balanced case. Positive would be it's overly excited, negative it's overly inhibited, and the global balance is just the average over nodes of the local balances. So one thing you note here that in this slide, there are a lot of choices that you can make in setting up this reservoir, right? I have a sigmoid function. The steepness might matter, the threshold might matter, the scale of the adjacency matrix, so the overall spectral radius. Lots of choices that matter. And there's some principles in the literature for setting up the reservoir. Some great general guidelines from this paper by Lukosevicius and Jaeger from 2009. A really nice theoretical paper by Bolt from 2021 on explaining why reservoir computing works so well for forecasting chaos. And then this question of, do reservoir computers need to be at a critical point or at the edge of chaos? There's been some work in this area. The answers, I would say, are not entirely clear sometimes. And then also I want to note that this edge of chaos criticality is different than this avalanche criticality that I was talking about earlier. So what's the bottom line here? There's some good guidelines to setting up the reservoir network, but a lot of open questions. And the hidden the hidden part of when you see, success of reservoir computing in predicting dynamical systems is that we train on the one-step predictions, but what happens is we do hyperparameter tuning to figure out, okay, well, what are the best features of the reservoir that will give us good one-step predictions, and actually give us longer-term predictions in the closed loop. So it's not generally, when people use reservoir computing, they're doing a lot of hyperparameter tuning that is somewhat not in the spirit of, oh, we're just drawing from this complex network repository. So what's different in our studies versus the typical RC implementations? So typical RC implementations, they really do have essentially a balance of excitation and inhibition. So there's an equal distribution of positive and negative links in the reservoir. There is heterogeneity. Typically we have that there's heterogeneous link weights on both the internal reservoir links and the input weight matrix. When you just make the reservoir links 0 or 1 or 0, 1 and -1, your performance is substantially degraded. But as I said here, the hidden part that doesn't get talked about enough, in my opinion, is that there's still this optimization of hyperparameters. So the reservoir link scaling, thresholds, the input weight scaling, etc., for each task. And so what we want to do here is we're going to think particularly about one. You can think of it as a hyperparameter, varying the balance between excitation and inhibition and how that affects performance. And we want to particularly look at the level of local EI balance. But we're also going to consider heterogeneity and some other features of the reservoir, with the goal of trying to identify if we can develop some heuristics for constructing networks that are robust across tasks that can reduce this hyperparameter optimization. So what happens when we vary the inhibition in the system? So here I have a constant number of nodes and links, and my excitatory links and my inhibitory links have the same strength. So this is different than in the brain, where inhibitory links tend to be about 4 times stronger than excitatory links, but then there's many fewer of them, so you overall have something that's close to balanced. But here, our setup, we have a constant number of nodes and links, and then we look at different fractions of inhibitory nodes. So 0% inhibition in the first column, 20% in the second column, and so on. Our links structure adhere to Dale's law that excitatory nodes all have outgoing excitatory links. And what we see here is in my top row, I'm looking at the firing rate. And in the bottom row, I'm showing the memory capacity in these networks as I vary 2 hyperparameters, the overall reservoir link scaling and the threshold, the firing threshold. If we have only excitatory nodes, so in my first column, I have this transition, basically, this sharp transition between all the nodes firing or all the nodes being at 0. And if I look at performance of memory capacity below that, I only get good performance like quite near the phase boundary. But by contrast, as I increase my inhibition, I get stronger performance over a wider region of hyperparameter space. And what we find in general is that the balanced and sometimes over-inhibited regions are what give us the strongest performance. So here, what I want to do is, so there I showed you 4 different snapshots of different excitatory inhibitory balance. And now I just want to have excitatory inhibitory balance as one of my hyperparameters, and then my threshold is the other hyperparameter. And I've fixed the link scaling, and I'm just varying the global balance by varying the mean strength of inhibitory links. So my excitatory links are kept constant, and everything else is kept constant on the horizontal axis. I vary the threshold on the vertical axis. And I get this phase diagram in my firing rates in the upper left. I have a region where all the nodes are saturated. That's not going to be good for information processing. Similar when they're all silent, and also a region when they're oscillating in lockstep, which is, and then if you see in my third case, okay, well, how does this correlate with some task like a memory capacity task? Well, it's in these regions in between the silent, saturated, and oscillatory that I get the best performance. But one thing to note is that I don't just get good performance at those critical boundaries. I get good performance over a wider region. And in the center here, I'm plotting the mean neuronal entropy. And if we're comparing the center plot and the one on the right, the performance plot, we see that good performance requires high mean neuron differential entropy. I need the neurons to be doing interesting things, but of course, high entropy isn't going to be a sufficient condition for good performance. Okay, so on our previous slides, what we've talked about so far is just in the phase diagram where I vary my excitatory inhibitory balance. Where's a good place for, if I'm just using that as a hyperparameter, what's a good place for performance in that case? Actually, before I do this one, I should say that this memory capacity performance graph, we see similar visually similar plots like this for time series prediction tasks. But what if I want to not tune my excitatory inhibitory balance, but I want to let the input strength self-adapt towards some level of local balance? And we use the following rule that their neurons each neuron has a target firing rate. Now, by saying that, I've introduced a new hyperparameter. But in introducing this one, I've done it so that maybe I can get rid of more than one other. So my plasticity mechanism is as follows. If a neuron fires more than its target firing rate, the incoming inhibitory links are raised by a small amount. And when the opposite occurs, the inhibitory links are lowered by a small amount. So the idea here is if the target firing rate is intermediate, this should lead to a network with a configuration of good performance. So basically, the synapses get modulated so that we don't get nodes that are either in this silent or saturated regime. And this involves a two-step training process. So first, I feed the input through once, and I allow the links to adapt, the reservoir links to adapt. And then I feed the input through again, and I train the output weights. So this first process is really quite quick, this link adaptation process. So I haven't really changed the computational complexity of the problem of reservoir computing. So here I'm showing if I start from different configurations of networks where my mean local balance, I'm plotting the mean local balance as a function of my adaptation time steps. You see that I'm getting to this globally balanced case. And in this case, I'm setting the target firing rate equal to a half for all nodes. So it draws it to this locally and globally balanced case. And notice here that even when I start out with a mean local balance of 0, my adaptations are still doing something here. So that's this like yellow-green curve. Just because the global balance is 0, I still have quite a spread in the local balances initially before my adaptations. And then if I look at my memory capacity as a function of time, if you look at this green one, it was globally balanced initially, but it improves dramatically still by creating this local balance. So we see that the plasticity drives the reservoir towards balanced regimes and improves memory. So after adaptation for local balance, performance is substantially improved regardless of where I started. But like I said, okay, so I introduced this choice of target firing rate, so a new hyperparameter. So what am I doing in my non-adaptive network versus in my adaptive network? So in my non-adaptive network, and my best performing non-adaptive network are these dashed lines, and I'm showing you 4 different tasks. In my non-adaptive network, I optimize the input scaling and global balance. So I'm optimizing those parameters. And in my adaptive network, I'm optimizing my input scaling, and the target firing rate is the same for all neurons. All other hyperparameters are set at defaults. And so what you see here is that we get much better performance for appropriately chosen target firing rates. Our performance is substantially increased. Um, but we still need to reduce the number of hyperparameters. We still want to reduce the number of hyperparameters we optimize over. And in fact, sorry, as I was speaking, I realized I had an error on the last slide because I omitted one of the hyperparameters that gets optimized for the non-adaptive case, where I'm doing basically standard reservoir computing, but one of my hyperparameters is this EI balance, and my other 2 that I optimize are input scaling and global balance, and I leave everything else the same. But then if I include the adaptation, I just have 2 hyperparameters that I'm going to optimize: the input scaling and the target firing rate. The threshold I've set, and I'm not optimizing that. And then you see the green, the homogeneous adaptive, is a big improvement over the best performing non-adaptive. So hyperparameter optimized non-adaptive. But I can also say, oh, can I reduce hyperparameter optimization further by instead of optimizing the target firing rate of neurons, can I just say, okay, I'm going to pick a distribution that seems like it would be reasonable. So we consider a distribution of target firing rates in this slide with a mean of 0.5 and a standard deviation 0.2. And what we see is that the heterogeneous adaptive networks, the green dashed bars, offer similar performance as the best performing homogeneous networks with 1 fewer hyperparameter to tune, which is sort of my goal here. I don't like this idea of hyperparameter tuning. It's a very under the rug, hidden part of reservoir computing. And if we want to leverage the inherent complexity, shouldn't we be able to think of what kind of complexity we want to draw from? So if we look a little bit about the neuronal properties here in our first column, in our globally balanced non-adapting RC, we have these widespread of firing rates and local balance, but a number of neurons, so I'm looking at the firing rate on the horizontal axis, a number of the neurons are sort of stuck close to the silent or saturated regime. And if we do this homogeneous adaptation, the firing rates, they all get to the target firing rate, but they're not all like at the target firing rate all the time, because that would be a very ordered state. And in fact, here we see that we have, in the second panel, we have high entropy neurons. So they're very close to this 0.4, and they're making small movements about 0.4 in time. But if I introduce this heterogeneous adaptation, it gives me kind of the distributions I'm looking for in terms of my local balance and particularly in terms of my neuronal entropy. I'm able to have this high entropy population of neurons that I can draw from. And so, one last thing I wanted to mention here. So let's take a step back here. What we did is we looked at what happens if we say, okay, one of the hyperparameters I want to tune is something that people think a lot about in neuroscience, which is the balance between excitation and inhibition. And it's typically just fixed in our reservoir computing. And so we saw that that can make a big difference. And if we say, okay, that's going to be one of the hyperparameters we tune, and we're going to tune it along with a few other hyperparameters. Our non-adaptive best performing RC is in blue. Then we introduced these adaptive RCs. Those are the solid green bars, and the heterogeneous adaptive RC is the green striped bar. So we got similar performance in those cases, and the heterogeneity eliminated some more hyperparameter optimization. But in fact, I actually don't have to even do this slow adaptation, right? I can just say, all right, well, what is the design principle that I'm trying to achieve? And the design principle I'm trying to achieve is this local balance is at a certain rate, is towards a certain firing rate. So I can just create a network and then rescale all the inhibitory links so I achieve that local balance that I'm looking for. And so that's what we have in orange and orange stripe. So the best performing in orange, or the heterogeneous, which eliminates another hyperparameter. And so this gives me computational efficiency. And we see that it performs very similar to the adaptive case. So, summary of what I've tried to convey here. If we think about this landscape of flexible, data-hungry machine learning to very efficient, structure-guided machine learning, reservoir computing, it sits somewhere in between, and it draws from rich implicit dynamics in the reservoir with lightweight training. But even though it has lightweight training, the problem of setting up that reservoir, having the right hyperparameters for it is an important problem that gets glossed over. I also touched on how we can combine reservoir computing with these structure-guided models and take some of the advantages of both, especially for cases when the structure-guided models might not be so appropriate, but having a bit of them really improves. Oh, and I should say, I talked about this paper of ours on hybridizing traditional and next-generation reservoir computing. Two former students of mine also wrote a paper on hybridizing hybridizing traditional reservoir computing with Cindy. So for those of you who might be interested in that, Wickner and Patel are co-authors on that. And so what we saw there is that these hybrid models really give us a lot of benefits from both sides. We can make smaller reservoirs. It improves robustness across tasks and conditions. And then we want to think about some principles from some brain-inspired computation. And one thing the neuroscientists think about is this balance between excitation and inhibition. And if we think about, well, if the balance is set at a certain level, we saw that reservoirs perform best in the balanced or slightly over-inhibited regimes and show reduced sensitivity to many hyperparameters in those regimes, particularly in the over-inhibited regime, that if you're in that regime and you vary your hyperparameters, you have less sensitivity. But then we thought, okay, well, what if we don't want to vary this parameter? So What if we want some sort of plasticity mechanism that is inspired by biological neural networks that drive reservoirs towards appropriately balanced regimes? And we show that this improves memory and forecasting performance. And we showed that if we put in heterogeneity in these target firing rates, it further reduces tuning requirements and it supports adaptable internal dynamics. And then finally, in the end, we were very motivated by this idea of plasticity, but if you're just coming at this from a design principle, well, actually, you can just design a system that has this local balance in it and get, the same types of improvements compared to these networks that have a wider distribution of balance. And sort of the lesson here is sometimes you really want heterogeneity. Like for instance, you want heterogeneity in your link weights. You want heterogeneity in the firing rates your neurons in your reservoir achieve. But in fact, the heterogeneity in your local balance can be detrimental. And so, too much heterogeneity in your local balance can be detrimental when you get into these sides where you want to avoid these silent and saturated regimes, and too much heterogeneity can push you into that realm. So it's all a question, our basic idea here is, well, what can we do inspired from the brain to improve our reservoir computing? And I really would say we've only made some first steps in this direction, and there are a lot of remaining open questions. So with that, I'll stop, and I am very happy to take questions.
Thank you very much for the presentation. Yeah, so open questions to the room or over Zoom at this point. All right, I can get us started with a question. On this slide here, you mentioned heterogeneity in target firing rates. And I think earlier you mentioned how there was this distribution of target firing rates that was chosen to be reasonable. Like, how do you choose that distribution?
We used a beta distribution. And we didn't play around too much with optimizing it. We were drawn to this from distributions of activity patterns in the brain. There's a wide range of activity patterns. But we didn't play around. I mean, it would be an interesting question in terms of like, what is the appropriate distribution of those target firing rates? And you asked this, and so it sort of brings up some related work that I'm quite fond of that also looks at heterogeneity in reservoir computers. It's by Tanaka et al., and they look at heterogeneity in the timescales of individual neurons. So some respond very fast and some respond much more slowly. And so it's a similar kind of principle. And this is a very nice piece of work. But again, they looked at just one distribution and showed, they had a lot of benefits. But in terms of thinking about, what kind of distribution do we really need? It's similarly unclear.
Cool, thank you. Any other questions? All right, well, I have another question. When you talk about the hybrid RC NGRC models, one of the advantages of that hybridization was that you could deal with sparser data, like you could have larger delta T in your data. Can you give a rough estimate of how large of delta T and sort of when you could push that to breaking even the hybrid RC NGRC?
Yes. So that's a good question. So, okay, in the Lorenz system, how far? I mean, certainly, let me look at, I'll put this up. So our delta T, you can kind of get a little sense of it looking at like the bends in these trajectories. Um, but we're still sampling when we're on each lobe of our attractor. We're sampling a few points on each lobe before we switch over. But that is still quite large. I mean, you're sampling, it's got to be smaller than the Lyapunov time. So the time over which so for a chaotic system, the time over which trajectories will diverge by a factor of E. So it's going to be smaller than that. And I guess that's about your window of where things are going to break down, even for your straight RC or for your hybrid model. But that is much, much longer than your integration time scale. Where, some like you can kind of think about if we look at this NGRC, a certain setup, the NGRC, you can sort of think of like an Euler method almost, right? So that's going to work. If you have the right terms, that's going to work really well if your time step is small, and it's going to break down if your time step is larger.
So for the Lorentz system, I think I remember that the largest Lyapunov exponent is something like zero point 0.9
Yeah.
in classic cases. And so for the simplicity of question, let's just say it's one, and then maybe, so you're saying that with the hybrid RC, NGRC models, you could potentially push delta T up to say zero point 0.5, zero point 0.6?
You can definitely be in that range. Yeah.
Okay.
Yeah. I mean, okay, let me just say point two. I don't I have visions of the point two stuff. I think point five would still work.
Okay,
But I can't, yeah, don't quote me on that.
cool. Thank you. Any other questions? All right. Well, thank you very, very much for your time. This was a really, really interesting talk, and I have some ideas here, and I'll be in touch with you outside of this context.
Wonderful. Thank you.
Thank you.